So we are now into the operation of excimer laser. But before moving any further, let me very briefly tell you as to why from a conventional atom or molecule you cannot obtain coherent light at ultraviolet wavelengths or even shorter. You see, from Bohr's theory, we know that the spacing between two adjacent energy levels abruptly reduces as the electron's energy increases. That means E2 minus E1, where E1 and E2 respectively are the electron's energy and the n equal to 1 orbit and n equal to 2 orbit. This is much more than E3 minus E3 minus E2, which is again much more than E3, E4 minus E3, and so on. This basically is a manifestation of the dependence of energy, inverse squared dependence of energy on the quantum number, principal quantum number n. Because of this happens. And as this happens, what is the result of this? The result is this. You see, the large difference of energy between n equal to 1 to n equal to 2, this transition can give you lambda, which can be very short. It can go to UV and even VUV. While this difference being much too less, it can give light visible infrared. Surely from this transition you cannot get ultraviolet. So if you have to get ultraviolet light, you will have to use this transition from E2 to E1. Now in the beginning, all your atoms, suppose we are considering the case of atom, are residing here. Therefore, to create population inversion between this level and this level, you will have to take at least half of this to this level. And you can of course use this level and take it. You can of course use this level. First you take it here and then bring them down here. But create population inversion and maintaining population inversion will be a Herculean task. And it is not at all practical. And even if you take the case of a molecule also will have its electronic energy levels, and which will also follow the same pattern, and you cannot get an ultraviolet laser based on a conventional atom or molecule. Now let us turn our attention to excimer. This is the ability of a rare gas atom to form a molecule only in the excited state, made possible to build an efficient ultraviolet laser. As the ground state of the molecule does not exist, molecule doesn't exist in the ground state because the rare gas atoms don't form molecule, you cannot form molecule. So the lower laser level, if this is your lower laser level, it is initially 0. Population of this level is 0. So if you can make a molecule in the excited state, then the moment molecule is formed, you have created population inversion, is established on this transition. And if you place this inverted medium, which is called excimer, this will result in the emission of coherent light in the ultraviolet region of the electromagnetic spectrum. The invention of excimer laser is credited to Monilal Bhaumik, an Indian-American physicist turned philanthropist and a best-selling author. All right, let us try to understand the underlying physics of an excimer. As I said, an inert gas atom cannot form a molecule because its outermost shell is completely filled with electron. You know that from your high school days. That is why they are called inert gas atoms, like helium, argon, xenon, krypton. When two such atoms approach each other, a repulsive force sets in that in turn pushes and keeps them apart, inhibiting the formation of a molecule. They cannot form a molecule. However, there will be a complete turnaround of the situation if these atoms are first electronically excited and then made to interact. So if you electronically excite it, then in the excited state, its electronic shell is not full, it is partially full. As the outer shell is now partially filled, they will now pull each other to form a stable molecule in the same way that it happens during the formation of a conventional molecule. The resulting molecule is essentially an excited dimer and therefore abbreviated as excimer. See, if you have, say helium, you have excited helium. So it is now chemically active and it combines with another helium, excited helium atom. So two identical helium, when they combine, they will form helium molecule in the excited state. So it is a dimer, excited dimer. Excited dimer. Same atoms. So we call it excited dimer. So it can be abbreviated as excimer. Excimer. Excited dimer. Exci. Let us consider xenon as our rare gas atom. So we use xenon in suppose a discharge tube. You take xenon in the discharge tube and put in voltage, two ends, and you create electron. Electron will have kinetic energy. You already know it. In a discharge, electron will acquire kinetic energy. And then this electron, when it collides with xenon, this will be an inelastic collision. Part of the kinetic energy of the electron will go to xenon, and its internal energy, and xenon will be excited. An electron will move with less kinetic energy. This is creation of an excited monomer, only one. It is excited monomer. Then when two such monomers combine, because they are now chemically active, their electronic shell is not full. So then they form molecules just like the formation of any other conventional molecule. So then it becomes a excited dimer or excimer. This is now excimer of xenon. So the excimer of xenon that can be denoted as Xc2 star, that is excited, is none other than an electronic excited state of the molecule xenon. Because this doesn't exist in the ground state, but in the excited state exists. The ground electronic state of which is so short-lived that it is considered to be non-existent for all practical purposes. This essentially means that the creation of even a single xenon 2 molecule in the excited state will result in a population inverted condition. So this is the ground state, n equal to 1. This is the excited state, n equal to 2. So you have created xenon 2 plus here. However, this xenon molecule in the excited state cannot exist indefinitely with its excitation energy and releases it as a UV photon by making a quantum jump to its ground state that disintegrates into two xenon atoms in a flash. So this xenon molecule in the excited state just drops down to the ground state and releases this excitation energy spontaneously as a photon. Now, as soon as the xenon molecule comes to the ground state, it will immediately split into xenon to xenon atoms in a flash. because it doesn't exist there. This spontaneously emitted photon, this photon, can initiate stimulated emission. Now it will stimulate another excited xenon atom, xenon molecule, stimulate emission, and in turn lasing in these excited xenon dimers. So from one, you will create two identical photons. They will stimulate two more xenon molecule in the excited state. And as the empty ground state allows realization of population inversion and its sustaining with minimum effort. And the moment it drops down to the ground state, it immediately splits. So the population of the ground state is always considered to be zero. So this allows realization of population inversion and its sustenance with minimum effort. Just as the electronically excited xenon combine with another excited xenon to form its excitement. When two xenons combines in the excited state, they form excited dimer, that is excimer. It can also readily form a molecule with an atom of another species that is not inert. So what it says is that you have xenon in the excited state. Now instead of combining with another xenon in the excited state, it can combine with, say, another atom, normal atom, which is not inert. So it will form xenon of that atom in the excited state. Not necessarily it has to be always dimer, it can be another atom also, which is not inert. So calling this molecule an excimer will be a misnomer. We cannot call it now a excimer because it is not a dimer, it is not an excited dimer, as it is more complex than a simple excited dimer. And although less common, lasers based on such variants of the excimer are called exciplex laser. That is excimer complex lasers, excited complex lasers. So these are called exciplex. As a matter of fact, noble gas halide excimer lasers. Halide means that A is a halide, as a halogen. So it could be chlorine, fluorine, bromine, etc. So noble gas halide excimer lasers are more popular from an application point of view than excimer. They are also high repetition rate compatible and capable of delivering both higher average power and energy per pulse. The excimers based on dimers usually operate at shorter wavelength, and these are some examples of rare gas dimer lasers, which shows different dimer lasers and their operating wavelengths. And these are some rare gas halide lasers and their operating wavelengths. As it can be seen, the excimer based on dimers usually operate at shorter wavelengths lying in the VUV region of the electromagnetic spectrum. Their wavelengths, all the wavelengths are less than 200 nanometers. They lie in the VUV region. And rare gas halide based excimer lasers and rare gas halide lasers, on the other hand, with the only exception of argon fluoride laser, operate in the UV region because their wavelengths are all above 200 nanometer. Additionally, rare gas halide based excimer lasers are relatively more energetic than their rare gas dimer variant. They can give more energy can be obtained from rare gas halide laser compared to their rare gas dimer variants. Let us try to understand operation of a noble gas halide laser. So the majority of the excimer lasers sold today are meant for the use either in medicine, primarily eye surgery, that is LASIK eye surgery involving cornea, which I told you a while ago, or in the fabrication of integrated circuits by photolithography in the semiconductor industry. That is, you create nanochips, nano integrated circuits. Energetic argon fluoride lasers possessing the shortest wavelength in the family of noble gas halide lasers are best suited for both these applications, that is photolithography application and LASIK eye surgery application. We will therefore describe here the working of an argon fluoride laser that is the rare gas halide laser, the operation of a majority of the excimer lasers will follow the same methodology. The argon fluoride laser makes use of three gases for its operation. Normally a buffer gas, usually helium or neon, constitutes the majority, that is almost 90% or more of this gas which are taken, gas mixture. While argon and fluorine together form the rest of the mixture. So if helium is the buffer gas, helium is even more than 90%, while argon plus fluorine together is about 10%. The buffer gas does not directly participate in the process of lasing, but plays a crucial role in the operation of the laser. So they are often called even surrogate gas. You have seen even in helium neon laser, helium performs the role of such surrogate gas, and it performs the same role in the operation of this argon fluoride laser as well. The electron environment that is prerequisite for the manufacturing of the electronically excited argon fluoride molecule is usually created by subjecting the gas mixture to a high voltage discharge. You have to create electrons. So the lasing process goes like this. The lasing cycle begins with kinetically energetic electrons present in the discharge, because in the discharge electron will acquire kinetic energy. You now know it very well. It will collide with ground state argon atoms and fluorine molecules. So when it collides with ground state argon atom, it has kinetic energy, so argon will go to the excited state at the expense of the kinetic energy from this electron, and the electron now will move with less kinetic. The electron can also ionize this argon, so argon ion will be created in the discharge, and you will have now two electrons. The collision results in both excitation and ionization of argon atoms, as well as giving rise to the splitting of fluorine into constituent atoms together with the formation of negative ion of fluorine. But how does the argon fluoride, halogen fluoride forms? We'll come to that. So the buffer species performs the role of a third body to facilitate further collisions among these freshly generated species, leading to the formation of electronically excited argon fluoride in the excited state. The sequence of collision is nevertheless complex, and the two likely channels for the formation of argon fluoride in the excited state are these. One is that argon ion and fluorine ion, in presence of helium, they combine into argon fluoride, that is rare gas halide, in the excited state, and helium is just performs the role of a buffer here. Without helium, this formation will be very, very improbable. See, in this, the argon and fluorine ion combine to form a single species. The presence of buffer atom, helium, performs the role of the third body to allow momentum conservation. Without helium, momentum conservation will be very difficult, and this reaction will be very, very improbable. For example, suppose let us consider a case in which argon, this is X direction, travels in the X direction, and fluorine also travels in X direction, and they combine and form argon fluoride, that is in the excited state. Now, if momentum has to be conserved, in this scenario, it can be conserved if and only if the argon fluoride also travels in the X direction, because both these atoms have momentum in the X direction. So in order to conserve momentum, argon fluoride will have to travel in X direction. If it travels in any other direction, then it will have a component of momentum in the y direction. While before the collision, there was no component of momentum in y direction. So argon fluoride cannot travel in any direction but x direction. So this is a big constraint and comes in the way of formation of such single species after the collision. So presence of helium takes care of this momentum. So whatever momentum deficit is there, electron either takes it or supplies it. Helium either takes it or supplies it. The above kinetic processes are more probable at higher gas pressures, as it presents better collisional environment, and consequently the excimer lasers operate at high pressures, usually exceeding an atmosphere. Only at high pressure such collisions will be more probable. So now you know that we already know from our past knowledge, we have studied electric pumping of gas lasers, both CW and pulse types. We know now that stabilizing a high pressure gas discharge is not possible in the continuous mode. Therefore, mandatorily an excimer laser will operate in the pulse mode. And because the operating pressure is very high, more than atmospheric pressure, you cannot have a longitudinal discharge. We know that a high pressure laser cannot be operated in longitudinal mode. So it is essentially operated in transverse mode. So it is essentially operated in transverse mode. That is, the discharge is a transverse discharge. Okay, I'll come to that. Essential to transfer energy stored in the discharge condenser homogeneously into the inter-electrode gaseous volume. Now, so how do you do it? You essentially, this is your, these are the two electrodes. And you have, this is your chamber, and of course you have a mirror, and there is a partially transmitting window, and you have a power supply. You charge up a condenser, this is a switch. When the condenser has been charged to the appropriate voltage, this switch closes and the condenser discharges its energy into the load. That is how you operate such a discharge in the a transverse discharge gas laser, such as this argon fluoride laser. But for typical operating condition, this laser requires a discharge duration which should be around 50 nanosecond or even shorter. If the discharge duration exceeds 50 nanosecond, discharge will arc. That means all the energy stored in the condenser should appear in the discharge within 50 nanosecond. Now, if the discharge loop, it contains the switch, then all this long circuitry, then the inductance is going to be pretty high. And with high inductance, you cannot have a very rapid discharge, short discharge. So often what is done, you have another capacitor here, which is called a peaking capacitor. And the moment switch closes, first the charge from this capacitor is transferred to this. This gets charged. It is initially not charged. And then this condenser transfers its energy into the load. So then the loop inductance becomes very small and you can get very fast discharge. That is how you actually operate such a laser. You have to get very fast discharge. For the typical operating condition of an excimer laser, the discharge tends to degenerate into arc if its duration exceeds 50 nanosecond or so. Handling, and there are other challenges. Handling and disposal of the extremely corrosive halogen gases, the use of which is mandatory in the operation of inert gas halide lasers, is another major challenge here. The entire laser head that comprises lasing chamber, the discharge electrodes, the gas flow circuitry comprising of a heat exchanger and gas blower must therefore be made out of halogen compatible material. Needless to say that building an excimer laser is both more involved and expensive in comparison to most conventional gas lasers. Excimer lasers intrinsically possess high gain primarily for the following two reasons. A very rapid discharge, mandatory for, as I said, achieving low discharge, causes excited level population to build up very rapidly. That means gain builds up very fast. An excimer, or more aptly the exciplex, after making a transition from the excited state to the ground state, dissociates almost instantly. This results in very high gain. This allows excimer lasers to laser with almost no requirement of cavity mirrors of high reflectivity, which is normally mandatory for conventional gas lasers. You see, and you know that for operation of a laser, the gain must be above the loss, otherwise lasing would not be sustained. So you have the active medium and you have the two mirrors, one is fully reflective, the other is partially transmitting. And suppose this is your gain. And depending on the transmission loss, so for most of the conventional lasers, the loss is about 10%, transmission loss. So the reflectivity will be about 90%. So on the gain, the loss, if you plot, it will be a straight line because this is frequency, this is gain. As the loss is independent of frequency, it can be represented as a straight line. Suppose if you increase the transmission, suppose you make it 40% and this is 60%, then the loss would be high. Loss line may be located here. So loss becomes more than gain. So it will not less. But for excimer laser, the gain is so high, even the same I'll show. So the gain can be like this for excimer lasers. And therefore, the cavity can be formed with one fully reflective mirror, that is 100%, and the other is simply glass window, which offers 4% from each side, Fresnel reflection. So with 8% reflection. So this will have 92% transmission and only 8% reflection, this glass plate. So loss line will be pretty high. Say this is the loss line. For this, the loss line may be here. But gain is so high that even with so high loss, it would still laze. So that is why this high gain allows excimer laser to laze with no requirement of a cavity mirrors of high reflectivity, which is normally mandatory for conventional gas lasers. An excimer laser is able to perform optimally with a fully reflective mirror at the rear end and an uncoated glass window at the front end that reflects only a small fraction of the light back to its cavity. All right, I end here today. This more or less brings an end to the course on excimer laser. I hope you have understood the underlying physics of operation of excimer laser. More importantly, how excimer laser can be made to emit coherent light at ultraviolet wavelengths.